Hello everyone, how is it going? Yes, welcome back to my course here on Discrete Mathematics, and today we are going to discuss about recursion. And recently we just had the courses on sequence as well as mathematical induction, and this recursion also has some similarities with that of sequence as well as mathematical induction. That's why we are just seeing this just after these two topics. Well, what is a recursion? Recursion, by definition, recursion means defining something such as a function in terms of itself. Is that confusing? Let's see, for example, f of x equals x factorial. So here we can define f of x as f of x equals x times f of x minus 1. Well, let's see a lot of other examples in the coming slides for this recursion, but basically this is the definition. Recursion means defining something such as a function in itself, in terms of itself. So for example, this recursion is a very powerful way of expressing programming stuff. For instance, if you really want to do some repeated task, then you can go for a recursive function because it just does the same thing again and again. Whenever you want to do that part, just call this function. We saw that is similar to the sequence as well. If you recall the sequence, we might have a for loop and then it repeats until that maximum limit. For example, if you have a summation, and summation, you have summation n equal to 0 to say x or x equal to 0 to n. In either case, you are going from 0 to a limit, and you always limit this by means of this, for example, using a for loop. Rather, in case of a recursion, as you have written a function, and this function, you can call this function again and again to itself until a condition is met, for example. And of course, we'll see an example later on, and we should be very cautious of using this recursion because at times your system might get into a deadlock condition, deadlock. We'll see about that later on. Okay, let's talk more about this recursion. Let's see a few examples of recursion here. Okay, we are asked to find f of 1, f of 2, f of 3, and f of 4, where f of 0 equals 1. So we have this function f of x in which you have this things are given to us. F of 0 is given, but f of 1, f of 2, 3, and 4 we have to find. Okay, here let f of n plus 1 equals f of n plus 2. So here is what given to us. So with this, we can find what is f of 1. So we just write f of 1 equals f of 0 plus 2. That is, in our case, it's going to be 3. The same way, if you want to find f of 2, then you're going to use f of 1 plus 2. So that again is going to be 5 because you're using f of 1 over there. The same way, f of 3 equals f of 2 plus 2. So that's 5 plus 2, that's 7. And f of 4 equals f of 3 plus 2 because we just use this form, right? F of n plus 2. So every time you just add 2 to it and you are getting a sequence of 3, 5, 7, and 9. And of course, if you are asked to find f of 5, f of 6, you would be able to find it. Yes, it's kind of calling this function to itself. That's the idea. For example, f of 1 calls f of 0 and f of 2 calls f of 1, and f of 1 is nothing but still the same function, right? That f of n plus 2, we are calling the same thing, we are calling the same idea, the same definition that is being defined for this function in this particular example. Let's consider another one where f of n plus 1 equals 3 times f of n. Okay, in this case f of 1 equals 3 times f of 0, that is 3 times 1. Remember that f of 0 is given to be 1, don't forget that. So you know what is f of 0, that is 1, and yeah, f of 1 is 3 times that. And f of 2, yes, you can guess that. F of 2 is f of 3 times f of 1, that is 3 times 3, that's 9. F of 3 is 3 times f of 2. F of 4 is 3 times f of 3. That's it. We are repeatedly calling the function to itself, and this is a very efficient way by which we can manipulate things. Recursion, more example, let's see here. Okay, the similar kind that you had here before. So now let's say that f of n plus 1 equals 2 power f of n. So let's consider this. F of 1 equals 2 power f of 0, that's 2 power 1, that's equals 2. And again f of 2 equals, we are calling f of 1 there, so 2 power f of 1 equals 2 power 2, that's 4. So you can repeat the same thing again. F of 3, you get the similar idea. F of 4, again you get a similar thought. So this is what a recursion means. We have another example here. F of n plus 1 equals f of n square plus f of n plus 1. So f of 0, again we can take that here, is given to be 1. So f of 1 equals f of 0 square plus f of 0 plus 1. So that is 1 square plus 1 plus 1, that's 3. And if you want f of 2, then you have to use this value there. So f of 1 square plus f of 0 plus 1. So in this case you have the values of, I suppose this has to be f of 1. So we'll just change this out. So in all these cases here, you're supposed to have 1, 2, 3. Okay, so that's right. So you're coming up with this f of 2 where we use f of 1, and for f of 3 we are going to use f of 2. So for example, f of 3 equals f of 2 square plus f of 2 plus 1, that is 13 square plus 13 plus 1, that's 183. And f of 4 equals f of 3 square plus f of 3 plus 1, that's 183 square plus 183 plus 1, that's 3673. So that's it. We have come across 4 examples of recursion. Okay, Fibonacci sequence. Even we can represent this Fibonacci sequence in terms of a recursive function. Okay, so as we have seen this one formula earlier when we talked about sequences, but this is a non-recursive function. But this one, this f of n equals f of n minus 1 plus f of n minus 2, this is a recursive function. So you could also represent by means of f of n plus 1 equals f of n plus f of n minus 1. So what is the main thing here is that we have to define the base case, because you know that Fibonacci series starts with 1, 1 and then goes on to add the previous values like 1 plus 2, 3, 3 plus 2, 5. So the base case here f of 1 is 1 and f of 2 is 1. So the first two functions are 1 and 1. Starting from 3 onwards, you are going to change. That is 1 plus 1 is 2, that is your f of 3, right? So the base case here is f of 1 and f of 2 is given to be 1. So sometimes people use f of 0 and f of 1. Yeah, it depends. So anyway, the basic thought is here to use the base case properly. So here is a simple code for Fibonacci sequence in terms of Java programming. So you can have a look at it. If you are familiar with C++ or Python, maybe the things might be different. And if in fact there are some packages available for if you are using Python or other tools like MATLAB and so on. So I'll skip this off. There are a few definitions in case of recursion. Recursions, tail recursions, and recursive. And in fact, we have also have things like transcursive functions. So this is an example of a bad recursive definition. You can see, like, you can define f of 0 is 1, f of n is 1 plus f of n minus 2. So in this case, you would be worried, like, just try to find f of 1. So this is like it takes you to some negative value and then you get stuck with that. Yes, that might happen. The same way, if you consider the second one, f of 0 equals 1, f of n equals 1 plus f of minus n. Again, it takes us to some negative values there. So anyway, basically, if you really want to define a function for negative integers or some other values of real values, you might be specifying it clearly. You have to define clearly. You have to also define the base case clearly, where to start and when to finish based on the application. Okay, defining sets via recursion. So for example, we just use the same two parts, like the base case or the basis step, recursive step. If you recall the induction method, we use the base case, then we use the inductive induction proof, and then the induction step we used, right? But here we use base case and the recursive step. So let's say this example, the set of positive integers, say 1 is an element of S, and recursive step is if x is an element of S, then x plus 1 is also an element of X. Does it sound familiar? Yeah, that's similar to the induction principle that we used to use, right? If you assume that for a certain value, if this is true, then we have to prove that for the next value, that is x plus 1, it has to be true. So defining sets via recursion, we have this, say for example, set of odd positive integers given. 1 is an element of S, and if x is an element of S, then we have to say, or we have to prove that x plus 2 is an element of S. So that's one other example. Here we have the set of positive integer powers of 3. 3 is this element of S, and then here you have x is an element of S, then 3 times x is an element of S. For set of polynomials, in terms of powers, set of polynomials with integer coefficient. So 0 is an element of S, then if p of x is element of S, then p of x plus c times x power n is an element of S. So here some thoughts, like c is element of z. Z here indicates the integers, and n is an element of z, then and n is greater than or equal to 0. Okay, recursion pros, easy to program, easy to understand. Of course, that's interesting, but we should be careful. I'll come back to this. Well, we see why I said we should be careful, because here it comes recursion cons. Okay, consider the recursive Fibonacci generator. Suppose you are writing a program to generate a Fibonacci sequence. How many recursive calls does it make? Let's say f of 1 equals 1, f of 2 is 1. We know these two are the base case, right? We have 1 and 1. Starting from the third one, we are going to use the formula. So f of 3 is 3. It's supposed to be, okay, we have 1, 1 and 2, 3, 5, supposed to be 8. F of 10 is 109, and we have f of 20 is 13529. F of 30 is 1,664,079. Then here comes f of 40, 204,668,309. So, well, here comes the next one, f of 50. That's 25,172,538,049. Well, this f of 100, that's too big for me. Well, you could consider having approximated to 7 times 10 power 20. Well, what's wrong with this? At 1 billion recursive calls per second, if your computer is quite fast enough, it would take over 22,000 years. Well, that's where we have to be careful when it comes to recursion. So at times the recursion also can lead you to some deadlock conditions, but that would also take over 10 power 12 GB of memory. That's huge, very huge. Well, this is one of the drawbacks that you have in case of recursion functions. Let me briefly tell you one more place where we should be very careful when we are considering the recursion. For example, in case of a recursive call, suppose you are writing a program and then you have function, say function f fun1. Say you have here this fun1 is here, and then you have another function, say fun2 is here, and while you are going through these functions, you are calling fun2 here, and when the fun2 or function 2 is called, the command goes over this place and it starts to execute, and what you are doing here is you are calling function 1. So when you call function 1, what happens? Again the call goes back to this position. So what's happening here? Function 1 calls function 2 and function 2 calls function 1. So this is what we call a deadlock condition. So the system gets stuck with this and it cannot able to get out of this kind of recursive calls. So that's where we have to be careful in order to avoid such conditions. In terms of electronics, if you are working with microcontrollers, at times we do have assembly programming by using recursive calls, and to avoid such things, people use a timer called watchdog timer. In the same way, we can also use a simple timer mechanism or we can just wait for a while, and if it does not come out of this function, we try to skip this particular function. We can code such a way. Or in other words, while these functions are going through this loop of calling one another, if a certain threshold is met, you should be able to come out either while you are here or while you are here. You should be able to come out of this deadlock state. Well, that's another problem that you can think of when you go on for programming. Okay, let's move on with this recursive part. Recursion versus induction. Consider the recursive definition for factorial. Well, f of 0 is 1, f of n equals n times f of n minus 1. So you have this f of 0 equals 1 as the base case, and here this n times f of n minus 1 is going to be your inductive step. So it's kind of this is a sort of induction. So you have base case and you have this inductive step. In this recursion parts, we call it as recursive step. Yeah, that's very similar to induction that we have talked about. Consider the set of all integers that are multiple of 3. You have this set given to you with 3, 6, 9, 12 and 15 and so on. So we say that well, x equals 3 times k, and k is an element of z positive, that is positive integer. So by recursive definition, the basic or basis step that you have here is 3 is an element of S, and recursive step is if x is an element of S and y is an element of S, then x plus y is an element of S. So that's one example that we have seen. Let's see recursion versus induction with another proof. Proof via induction. Prove that S contains all integers that are divisible by 3. So let A be the set of all integer divisible by 3, and show that S equals A. So we have two parts. One is to show S is a subset of A. The other one is A is a subset of S. Got it? I repeat this part again. We are asked to prove that S contains all integers that are divisible by 3. And we are saying let A be the set of all integers divisible by 3. So you have the set A which has all the integers that is divisible by 3. So we are asked to show or prove S equals A. To show that, there are two parts you can prove it. One is you can show that S is a subset of A and A is a subset of S. Well, let's say P of n equals 3n. 3n is an element of S. And then you have the base case P of 1 equals 3 times 1, which is element of S. So by basis step of this recursive definition, we are using this base case. And with inductive hypothesis, we assume that P of k equals 3 times k is an element of S. That is the inductive hypothesis. So we assume that that is true. And what is our next step? We are going to say the inductive step for P of k plus 1. We have to prove that for P of k plus 1, it has to be true. So P of k plus 1 equals 3 times k plus 1 is true. So let's see here, 3 times k plus 1 equals 3k plus 3. So 3k is an element of S by inductive hypothesis that we have seen earlier. Therefore, we have 3 is an element of S by the base case. We already seen that one as well. So thus 3k plus 3 is an element of S by recursive definition. So by means of we started with the inductive proof, but we have concluded with the recursive definition by showing that S is a subset of A. Now consider this similar step, use it for A is a subset of S. So you can try out by yourself which has the similar sets. So basically just we have proved that S contains all the integers that are divisible by 3, because we used another set A, and we assume that A also has a set of all integer divisible by 3, and then that's it, we proved it, right? And we showed that S is equal to A. So what we just do is the way we express this recursive form of proof. So let's see, we showed the base case to be true, we proved that is true, then we assume the inductive hypothesis as before. After assuming the inductive hypothesis, our next term is to prove the inductive step. Yeah, we proved the inductive step. So for inductive step, we showed that each of the parts were in S, the parts being 3k and 3. These are two parts that were there in S, and 3k has been proved in inductive. 3k is one of the assumptions, that is 3k is our inductive hypothesis or assumption, and 3 is a part of the base case. So these are the two parts we had. Yeah, so we showed that both parts were in S. We showed that 3k as well as 3 both are in S. By the recursive definition, the combination of those parts is in S. Yeah, so we had this both parts. So that's, if you want to quickly look at what's went through, you can just have a look at this, and you clearly see that we have proved it using the recursive definition. Okay. So this is what we have done. And this is also called structural induction. So when you prove things by means of a recursive definition, we can call that kind of proof as structural induction. So talking about the structural induction, so this is one of the convenient form of induction for recursively defining things. When used in conjunction with recursive definition, we have three parts. The basis step, show that the result holds for elements in basis step for recursive definition. So that's your base case. Then comes the inductive hypothesis. You assume that the statement is true for some existing element. For some element it is true. It is same as the inductive proof that we have seen earlier, the proof by induction. The third step is your recursive step, but in inductive hypothesis we usually this just means assuming the statement is true. So for some existing case we say that the statement is true, and for recursive step, show that the recursive definition allows the creation of new elements using the existing elements. So it allows the creation of new elements using the existing elements. That's the recursion, right? So here's the basic outline of what you have for this induction methods. You can see we talked about the weak mathematical induction, strong mathematical induction, structural induction. And the weak mathematical inductions is used for usually for basic formulas. and the basic assumption is that assume P of k, we assume P of k, and then we have to prove P of k plus 1 is true. So initially we have the base case, and then the step 3 is inductive step. So for the strong mathematical induction, usually formulate not provable via mathematical induction. So it's very hard to prove using the basic mathematical induction. So here we are going to assume that P of 1, P of 2 till P of k all are true. Then we have to prove for P of k plus 1 is true. The same base case and inductive step is applied. For structural induction, so only thing defined via recursion, we go for the structural induction. So we assume that is true for some old element or some elements that are existing, as we have seen here earlier. Some existing element, it has to be true for some existing element, and then the statement is true for a new element, the new element that you are about to create using the recursion. So it is true for the new elements created with the old elements. So that's what we have to prove, and uses basis step and recursive step. So basis step is similar to that of base case that we have for mathematical induction. Let's go further and see some induction types compared. So f of n is less than 2 power n. So we have to prove this one. So where f of n is the nth Fibonacci number, actually f of n is less than 2 power 0.7 times n, but we don't have to prove that here. We don't really have to prove this. So by means of definition of this Fibonacci, we know that f of the base case is f of 1 and f of 2 both are 1, and then the recursive step we have the same formula, f of n equals f of n minus 1 plus f of n minus 2. So the base case or the basis step, we show that it is true, because we have to show at first, this is very essential. So f of 1 equals f of 1 less than 2 power 1, that is 2. F of 2 equals 1 less than 2 power 2, that is 4. So here you can see there is some values that you have come up with, in which it doesn't really shows the actual base cases true for the given function. So if we talk about a function that is of 2 power n, then this is how it looks like. So why a weak mathematical induction? Suppose if you have f of k is less than 2 power k, then inductive step is f of k plus 1 is less than 2 power k plus 1. So f of k plus 1 equals f of k plus f of k minus 1. In that case, we know that f of k is less than 2 power k by inductive hypothesis. So that is an assumption that you have, and each term is less than the next term. Therefore, f of k is greater than f of k minus 1. So with this thought in mind, we can say that f of k minus 1 is less than f of k less than 2 power k. So therefore, f of k plus 1 equals f of k plus f of k minus 1 less than 2 power k plus 2 power k, that is equals 2 power k plus 1. So that's how it has been proven. So we are having this inductive hypothesis in which we have to prove it for a particular value k. Initially, if you go back and see in the previous slide, you might have noticed that we have to show for 2 power any value of n there. So here we are assuming that we have to prove for 2 power k. We assume that it is true for 2 power k, and then we have to prove for 2 power k plus 1. That's where we finally proved for 2 power k plus 1. So this is the overall proof that we have via mathematical induction. And how about strong induction? Strong induction, as you know, that we have to show for all values f of 1, f of 2, f of 3 till f of k, and then for inductive step we take that f of k plus 1, what is the next value. So initially for inductive hypothesis we don't have to prove, we just assume that it is true for all values, but for inductive step we have to show. So here f of k plus 1 equals f of k plus f of k minus 1. So we know that f of k is less than 2 power k by inductive hypothesis, but that is one of the assumptions that we have there. So with this in mind we can apply that values over here. So f of k minus 1 is less than 2 power k minus 1. Therefore f of k plus f of k minus 1 is less than 2 power k plus 2 power k minus 1 is less than 2 power k plus 1. So that's it. We have proved here for inductive step via structural induction, that is recursive steps. So we have this inductive hypothesis, we assume that f of n is less than 2 power n. Then we have this recursive step in which we have to show it's true for a new element n plus 1. We assume that it is true for the old element n, and we have to prove for the new element n plus 1. So we know that f of n is less than 2 power n by inductive hypothesis, that's the assumption, we know that it is true. Then for each term is less than the next, therefore we are saying that f of n is greater than f of n minus 1, right? The same principle that we have used earlier. We know that each term is less than the next term. So by that we are saying f of n is greater than f of n minus 1. Thus f of n minus 1 is less than f of n less than 2 power n, right? Yes, we are just using the same idea here. Therefore we say that f of n plus f of n minus 1 is less than 2 power n plus 2 power n, that is equals 2 power n plus 1. So if you want to of course last two induction methods as well as the first one all use the similar ideas. Just for your thought, you can just have a look at what is going on from the beginning, and you can see how this whole proof has been defined. So thus we have been proved it. So another way via structural induction is that inductive hypothesis f of n is less than 2 power n and f of n minus 1 is less than 2 power n minus 1. So that's the previous term there. The difference here is that we are using the 2 old elements versus 1 as in the last slide. So in the last slide we just used one previous element, but here we have f of n is the old element and f of n minus 1 is again another old one, the previous one, old element. So let's use this recursive step, show it's true for the new element f of n plus 1. We have n minus 1, we have n and n plus 1. N and n minus 1 are the old elements, so we are going to use those to prove it. So f of n plus 1 equals f of n plus f of n minus 1. So we know that by inductive hypothesis we know that f of n is less than 2 power n, that is true. So we know f of n minus 1 is less than 2 power n minus 1 by inductive hypothesis. Again, that's another old element, so we know that that's true. Therefore f of n plus f of n minus 1 is less than 2 power k plus 2 power k minus 1, that's less than 2 power k plus 1. That's it, it's proved. Well, then now let's go for a thought here. So this example, the structural induction proof was essentially the same as weak or strong mathematical induction proof. So it's hard to find an example that works well for all induction types. Yeah, it's not that much easier. But structural induction will work only, not only like structural induction will work on some recursive problems. So that's one of the advantage, right? Where which the weak or strong mathematical induction will not. So as far as we have seen, the structural induction will work on some recursive problems, whereas the weak or strong mathematical induction will not work on it. So that's the thought of the day. Yeah. So today we have seen about the recursion. So as far as the structural induction is concerned, things like trees, strings, we can go for structural inductions. And as we have seen today, a lot of interesting topics about recursion in general. So let's basically have this recursion definition examples, like give this recursive definition of following sequence. Note that many answers are possible for the following sequence. A sub n is equals 4 n minus 2. The terms 2, 6, 10, 14, 16, etc. can be obtained for A of A sub 1 equals 2, A sub 2 equals 6, and so on. So A sub n equals A n minus 1 plus 4. We have B, the another recursion you can come up with. A sub n equals 1 plus minus 1 power n. So we have the term 0, 2, 0, 2, 0, 2, etc. has been formed, in which A1 equals 0, A2 equals 2. So again you have this A sub n equals A sub n minus 2, the form. Okay. So third one is A sub n equals n times n plus 1. So we have the term 2, 6, 12, 20, 30, 42, etc. So we have A1 as 2, then An equals A sub n equals A sub n minus 1 plus 2 times n. Then we have another one, A sub n equals n square. So we have 1, 4, 9, 16, and so on for the squares. So A1 is 1 and An equals the A sub n equals A sub n minus 1 plus 2n minus 1. So these are some of the basic definitions, basic simple examples for recursion is given to us. So generally speaking, the things that we learned today all has to do with the recursion. We know what is the advantage of using recursion, and you know what is the disadvantage of using recursion, and we know we should be very cautious of using recursion, because at times we might go into some deadlock state. And now you found the relationship between the recursion and the weak as well as strong induction. So as we go with this recursive step, we call this kind of proof as structural induction. So structural inductions are good for recursive kind of problems, whereas weak induction and strong inductions cannot be applied on a recursive kind of problems. Well, that's a lot of information for today. I let you to work on some more examples, and if you have more questions, you can come up with those questions. As this is an online course, I encourage you to participate more by asking you some questions. You can post those questions if you like, and it's a good time that we have this discussion today. And until the next time, goodbye. Have a nice day.